Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to provide an overview of regression. We'll begin talking about linear regression models. Then we will discuss overfitting in linear regression and how it can be addressed using regularization techniques such as rich regression and the lasso. Finally, we will describe three different approaches to build nonlinear regression models. 1. Regression trees. 2. Ensembling techniques, including bagging, random forests, and boosting. And 3. Neural networks and deep learning. We're going to provide an overview. If you want details about each of these specific topics, you can look at the corresponding video or also at the book. Let's get to it. We're going to provide an overview of regression. The problem of regression is that of estimating a quantity of interest that we call the response from several observed variables that we call features. Here is an example. Here we have a data set where each data point corresponds to a county in the United States. And what we want to do is we want to estimate premature mortality, which is color-coded as shown here on the color bar, from two observed features. The first is the fraction of adult smokers in that county, which is represented in the horizontal axis. And the second is the median household income, which is represented on the vertical axis. Let's provide a probabilistic formulation of the regression problem. Probabilistically, we represent the response y as a random variable. This is why it has this squiggly line on top. Remember that this is how we represent uncertain quantities using random variables. We put a squiggly line when we write them. And the features are a random vector, because there are going to be several features, each of them a random variable, which we're going to stack in a random vector x. And our ultimate goal is to obtain a regression function h that for each possible value of x is going to map that to an estimate of the response y. How do we evaluate a regression estimator? A standard metric to evaluate them is the mean squared error, where we take the response and then we subtract the estimate corresponding to the feature vector. We take a square so that there are no cancellations, and then we average using the mean. This mean squared error metric can be optimized exactly using a very specific estimator, which is the conditional mean. There is no other estimator that can have a better mean squared error than the conditional mean. This is the conditional mean of the response given the feature. So for each value of the feature, this estimator maps of the feature vector. This estimator maps the feature vector to the conditional mean of the response given that the random vector that represents the features is equal to that specific value. Of course, in general, we're not going to have access to random variables and random vectors. We need to estimate the regression, we need to approximate the regression estimator using data. So here is a data set that has n data points. Each of these data points or examples encodes a feature vector and the corresponding response. Okay, so we have n pairs of feature vectors and responses, and from this we want to estimate, or we want to approximate, the regression function. A reasonable metric to evaluate a regression function on a data set like this is the residual sum of squares, where we compare each of the response examples to the estimate produced by plugging the corresponding feature vector into the regression function. We again take a square to prevent cancellations, and we sum over the whole data set. Here we're not averaging, we're summing, but essentially this is equivalent to the mean squared error metric that we mentioned in the previous slide, except that this we can compute on a real data set. And it turns out again that there is an estimator that is optimal with respect to this metric, and that's the empirical conditional mean of the response given the features. Let's take a look at an example to make this very clear. Imagine that we want to estimate the rating for a movie, which is Independence Day, from the rating of for another movie, which is Mission Impossible. In order to compute the empirical conditional mean on a data set, what we do is we take a look at all the people in the data set that gave a 1 to Mission Impossible, and then we average the ratings that they gave to Independence Day. And like this, we obtain this conditional mean estimator. Our estimate for the rating for Independence Day, if they have given a 1 to Mission Impossible, is going to be around 2.5. We do this for all the possible values of the feature, and that gives us a regression function. There's only 5 possible ratings. This gives us 5 estimates for the rating for Independence Day, given the rating for Mission Impossible. And this is absolutely optimal with respect to the residual sum of squares. So, are we done here? Can I just, pause the video or stop the video and go do something else? No, there's a catch. What I just explained works well if you have a very, very small number of features. But unless you have a very small number of features, it is actually impossible to approximate the conditional mean with a finite data set due to the curse of dimensionality. To explain why, imagine that we were trying to predict the rating for Independence Day from 100 movie ratings, instead of from just 1. How many different feature vectors would we have to consider in that case? Well, if we had, when we had just 1 rating to consider, then there were 5 possible ratings that could be given to that movie, so 5 possible feature values. But now we have 100 movies, there's 5 possible values for the first one, which we have to multiply with 5 possible values for the second one, which we have to multiply with 5 possible values for the third one, and so on and so forth, so that there's 5 to the 100th power possible feature vectors that we have to consider. If we want to be prepared for any possible feature vector that we can encounter in the future, then we would have to compute 5 to the 100 different conditional averages, as we explained in the previous slide. That's 10 to the 68 conditional averages. Of course, we're never, ever going to have even a fraction of that much data. We're going to have a tiny fraction of data compared to the possible feature vectors, and that's the curse of dimensionality. Because of that, when we encounter a new feature vector, it's very likely that it's going to be unique. We're not going to be able to go to our data set and say, oh, among the feature vectors that are equal to this exact pattern, what were their ratings for Independence Day? Let's just average them. Well, we're not going to find any, so we're not going to be able to do that. Because of that, when performing regression in the real world with a reasonable number of features that is not just 1 or 2, we're going to need to make some assumptions. And in the rest of the video, we're going to explain different methods that are based on different assumptions. We're going to start with linear regression, then we will talk about overfitting and regularization, and finally we will talk about nonlinear regression. In linear regression, what we do is we build a regression function where we just multiply each of the features by a constant that is learned from the data, then we aggregate by summing over all the features, and finally we add another constant that we call the intercept. Equivalently, we take the inner product of the feature vector with a constant vector that again is learned from data, and then we sum the intercept at the end. The linear estimator that has that form that is optimal with respect to mean squared error has a closed form that only depends on the covariance matrix of the features, which we have to take the inverse of, the cross covariance between the features and the response, which contains all the covariances between each feature and the response, and then the mean of the features and the mean of the response. This is optimal with respect to mean squared error. It's actually completely optimal if the features and the response happen to be jointly Gaussian, but it's not optimal in general because there could be a nonlinear relationship between the features and the response, and this estimator would not be able to capture it. We're going to talk more about this when we consider nonlinear regression later on in the video. But in general, we have data, right? We don't have the true statistics between the features and the response. So what do we do when we have a data set like the one I described before, where we want to estimate premature mortality from the fraction of adult smokers and median household income? Well, in that case, we apply ordinary least squares. where we minimize this residual sum of squares, a metric that I mentioned before, where we take each response in the dataset that we want to use to fit the model, and we minimize the error between the response and the corresponding linear estimate. We choose the vector of coefficients and the intercept that minimize this residual sum of squares. That's called the ordinary least squares estimator, and it turns out that it has a closed form solution that is very similar to the minimum mean squared estimator. Essentially, we just plug in the sample statistics, the sample covariance matrix where we had the covariance matrix before, the sample cross covariance where we had the cross covariance before, and the sample means where we had the means before. So let's see what this estimator looks like for our example of interest. Here in the vertical axis, I've plotted each of the counties. In the vertical axis, we see the premature mortality for each of the counties, and this axis is adult smokers, and this axis is household income. The model can be represented as a plane in 3 dimensions because it is linear with respect to the median household income and also linear with respect to the adult smokers. This is the plane that better approximates the data points in the vertical axis when we aggregate the error over all of the data points, and we consider the residual sum of squares. These are the coefficients that I learned from tobacco for income, and this is the intercept. We can also represent the model like this, where these are contour lines that are all straight lines because we have a linear model, and the estimate is a constant on those contour lines. This again is the linear model that best approximates the mortality with respect to the residual sum of squares. Now let's move on to talk about overfitting in linear regression and regularization. In order to do that, we're going to consider a different real data example where we want to estimate the temperature in Versailles, Kentucky, but now we won't only have 2 features. We're going to have 133 features that correspond to the temperature at other locations in the United States. If we have a lot of data and we compute the ordinary least squares model that we described before, this is what we see. So here I've plotted the coefficients of the ordinary least squares model as markers whose radius is proportional to the size of the coefficient. So, and they're situated at the location where these temperatures were measured. This is the response that we're trying to approximate. This is the largest coefficient at Bowling Green. You can see that it's very large. The second one is at Bedford. The third one is at Elkins. So what we observe, and the rest of the coefficients are very small. They're scattered all over the United States, very small. So we see that the ordinary least squares model learns to take a small number of locations that are close to the location of the response and just averages them, which is a very reasonable way of estimating the temperature in Versailles. This is what happens when you have a lot of training data. What happens when you have not so much training data? Well, this is what happens. Here, you have the number of training data in the horizontal axis. When we have a lot of training data, these are the coefficients which are represented on the y-axis. What we see is that there's 3 very prominent coefficients that correspond to Bowling Green, Bedford, and Elkins, these locations that were close to the location of the response, and the rest of them are pretty small, and this, as we will see in a moment, gives very good performance. But if you don't have a lot of data with respect to the number of features, which is 133, then you have a situation where there is an explosion in the other coefficients that are not geographically meaningful, where they flood, like basically they occlude the truly meaningful coefficients and they go bananas. They become very large and very small. And the reason that this is happening is that by doing this, because of the small number of data, the model is able to overfit the training data set, and we can see this because the training error becomes extremely small as the number of data approaches the number of features. This does not happen at all when the number of data are large. In that case, the training error is the same as the test error, which is computed on a held-out dataset that was not used to train the model. When we look at this regime where the training data becomes very small, the test error on that held out dataset is atrocious. So the model is completely overfitting the training dataset by having these large negative and positive linear coefficients. In order to explore this issue more in depth, let's consider a simulated dataset where the response is linearly related to the features that are stacked within this matrix, and there are some true coefficients which are going to be set to, in a moment we will see that they're going to be set to 1, 1, because we're going to have two features, and then we add some additive noise that is going to be Gaussian with variance, with a fixed variance. And everything is going to be centered to have zero mean. Now the question is, when is ordinary least squares going to produce a good estimate of these true linear coefficients? And again, there are some true linear coefficients because we're simulating this data. We're going to see that the OLS coefficients, the ordinary least squares coefficients that we obtain when we fit them to this kind of model have several important features, several important properties. First, they're going to be centered at the true coefficients. When we generate a lot of OLS problems by sampling from the noise vector Z, so we're going to sample from C over and over, and then we're going to take a look at the corresponding OLS coefficients. We're going to see that they're all going to be centered around the true vector of coefficients beta. But their variance is going to depend. It's going to depend on the number of data. As the number of data increases, the good news is that the variance is going to decrease. So the OLS coefficients are going to be a consistent estimator of the true coefficients as the number of data grow. They're going to converge to the true coefficients. However, when the features are collinear, and this happens very easily when the number of data is small with respect to the number of features, then the variance is going to be large in directions where the features have low variance. Let's take a look at what I mean by that. So first, this is an example with a relatively small number of data, but things are not collinear. And what we observe is some variance around the true coefficients, which are at 1, 1, as I said before. If we increase the number of data and keep things not collinear, then suddenly we're going to observe much less variance. As I explained before, we have theoretical explanations for all of this in the videos on OLS, in the video on OLS coefficients. If, however, the features are collinear, and by collinear I mean there is very little variance in this direction, the variance is mostly in this other direction, in the direction where we see small feature variance, boom, the coefficients explode. Why? Because this allows the coefficients to overfit the noise term that is not related to the features. And of course, we don't want that because this is just random noise that is not truly related that does not truly capture the relationship between the features and the response. So we have that problem. If there's a small number of training data or the features are collinear, then OLS produces large coefficients that overfit the training data. In order to avoid this, one can add an additional term to the ordinary least squares cost function. Realize that here we don't have an intercept because we're assuming that everything is centered to have zero mean. And that additional term penalizes the L2 norm of the linear coefficients to prevent them to become too large and thereby overfit the training data. Lambda here is a regularization parameter that determines the relative strength between these two components of the cost function. And this method is called rich regression. Let's take a look at what rich regression does for a simulated example where there's no noise explosion in this direction to overfit the data when the features are collinear. So this is what happens with OLS. There's this explosion in the coefficients when we sample the noise vector in our simulated model over and over. If you have a very small lambda in rich regression, it looks very similar. But if we push lambda up so that we're penalizing the magnitude of the coefficients, then suddenly we greatly reduce the variance of the coefficients. However, there's a price to pay, and that is that now they're no longer centered at the true coefficients. They're biased towards 0. And this becomes even more evident if we push the regularization parameter further up. The variance becomes very small, but there's a clear bias towards 0. So we observe that as the regularization parameter increases in rich regression, the variance decreases, and it actually decreases faster in directions of low feature variance, which is exactly the directions which are problematic for the ordinary least squares estimator, and this prevents overfitting. However, there is a price to pay, which is a bias towards 0. Let's see what happens when we apply rich regression to our temperature prediction problem, where when we don't have enough data, then we have this explosion in the coefficients that overfit the training data. Here I've fixed the value of the number of training data to be 200, which is in there, kind of at the middle of that interval that I highlighted. There's only 200 training points. If the regularization parameter is very small, what happens is the same as in ordinary least squares. A lot of the coefficients go bananas because they're trying to overfit the ordinary least squares term in the cost function. If the regularization parameter is too large, then everything is set to 0. However, in the middle, there is a sweet spot where rich regression is able to identify these geographically meaningful coefficients. And if we look at the test and training error, it actually is able to improve the test error with respect to the test error when of ordinary least squares, or equivalently of rich regression when the regularization parameter is very small, by preventing the overfitting that occurs here. Okay, you can see that the training error is larger as we push up the regularization parameter. Of course, eventually when everything is equal to 0, both the test and training error are terrible. So if we select the regularization parameter based on some validation held out data for every possible number of training data, we observe that we have solved our problem. So here we had this noise amplification resulting from overfitting. This is avoided by applying rich regression, and we correctly obtain an estimator that just mainly depends on a few locations that are close to the location of the response. But do notice that we still have a fair amount of coefficients that are non-zero, that are contributing to the estimate. This results in a better, this prevents this overfitting that we observe here. This is the overfitting of OLS. Now rich regression has much less overfitting, and as a result, the terrible, maybe I'll use the same colors, this terrible test error of ordinary least squares is much improved by rich regression on our real dataset. In some cases, you may want to actually obtain a linear estimator that only depends on a small subset of the features, because you believe that this will allow you to obtain a good fit and prevent overfitting, or because you want a more interpretable model that just depends on a small number of features. Equivalently, you want to find a sparse vector of parameters where most of the coefficients are 0 that still provides a good fit. This is the problem of sparse regression, and we're going to explore it with a variation of our simulated data where only one feature is linearly connected to the response. There is some additive noise, and the coefficient here is just equal to 1. And now we're going to fit this model with a spurious feature that is not linearly related to the response. Realize that it's not there anywhere, but we don't know about it. Ideally, when we fit the data, we're going to be able to figure out that only this feature is important. Again, the true coefficients are 1 for the true feature that is important and 0 for the one that is spurious and is not connected to the response. So now what happens if we sample this noise Z that has fixed variance? And let me remind you that everything is centered to have 0 mean. So we sample the noise over and over again, and we look at the coefficients. We would want the second coefficient to be 0, and the first one ideally to be as close to 1 as possible. So when we apply rich regression at first, so notice that the second coefficient is plotted here. So we would want the estimates to be on that line. They're definitely not when lambda is small. But now let's see if we apply rich regression and we push lambda up, because we know that this is going to make the coefficients smaller. Well, what happens is that the coefficients indeed become smaller, but they do not become sparse. They're not on this line. And there's a theoretical explanation of this, which is that ridge regression shrinks the coefficients, but it shrinks them in the basis of principal directions of the features. And you will have to take a look at the video on ridge regression to really understand that, or look at the book. But basically, that's why we in general do not obtain sparse estimates with ridge regression, no matter how much you push the regularization parameter. We can solve this, however, by replacing the L2 norm, penalty in ridge regression by an L1 penalty, and this approach is called the lasso, which is then combined with the OLS cost function, just like in ridge regression, and there's also a regularization parameter that determines the strength. So this is exactly like ridge regression, except that we're replacing the L2 norm squared by the L1 norm. If we do that for our simulated data, we start pushing the regularization parameter up so that the regularization takes effect, and boom, it works. Most of the coefficients are sparse, and they correctly identify that it's coefficient 1 that is actually linearly connected to the response, and coefficient 2 is not. If we have a value of the regularization parameter that is too large, then this is going to be very biased towards 0, but you can see that it's very sparse. So it still has the right sparsity pattern. Now let's take a look at what happens for the temperature prediction problem, and we're specifically interested in this regime where we don't have a lot of training data. Remember that here for ridge regression, if we had 200 training data points, then there was this sweet spot where we got a better estimate. If we apply the lasso instead, what happens is that we also get a better estimate there, and a lot of the coefficients are set to 0, in contrast to ridge regression, where they're small but they're definitely not 0. And as a result, the geographically meaningful coefficients are more prominent, which in our case makes a lot of sense. If we do this for all the possible numbers of training data, by selecting the regularization parameter using some held out data, we again observe that for ridge regression, many of the coefficients remain, they become small, but they don't become 0. And the geographically meaningful coefficients are not as large as when we have a lot of data. The lasso manages to correct for this, setting a lot of the coefficients that are not geographically meaningful to 0, and producing geographically meaningful coefficients that are larger, particularly the one for Bowling Green. As a result, for our specific data set, the lasso has less overfitting than ridge regression, and as a result also improves the test error. This is for our data set because it turns out that you can actually solve this regression problem with a small number of features, and when there's not a lot of training data, this really helps you to have stronger generalization. There might be other problems where you might want to use a larger number of features, and ridge regression may give better results than the lasso. Perfect. So now let's move on to nonlinear regression. To motivate nonlinear regression, we're going to use a running example where we want to estimate the temperature in Manhattan, Kansas, but now it's not going to be based on temperatures at other places. It's going to be based on the hour of the day, which we're going to encode as a feature that is between 0 and 23, and the day of the year, which is going to be another feature that is between 1 and 365. The training data are going to be temperatures from 2015, and the test data are going to be temperatures from 2016. This is the training data. So just to be clear, like this, like the end of January would be day 31, and this would be like noon, the 31st of January, let's say. That's the temperatures are color coded as indicated here. Notice that when we go from winter to summer, the temperatures increase, and then when we go from summer to winter again, the temperatures decrease. Similarly, with respect to the day, like at night, temperatures are cold. They get warmer as we go up here in the hour of the day, and then they become colder again. Why do I point that out? Because these are nonlinear patterns. This is the test data that has essentially the same patterns, but not exactly the same, because they're from another year. This is from 2016, and the training data is from 2015. So now we fit a linear model to the training data, which means we learn a coefficient for hour, a coefficient for day, and a linear intercept. Let's take a look at the linear model. It looks like this. And as you can see, the linear model has to increase with respect to both, or decrease with respect to both of the features. It cannot increase with respect to the day and then decrease with respect to the day, which is really what happens in the real data. It can only, like in this case, it increases when we increase the day for any fixed hour, and for any fixed day, it increases as we increase the hour. So it cannot capture these nonlinear patterns that are present in the training data. And because of that, it underfits the training data, producing a terrible training error of like an average of 10 degrees. And it also doesn't generalize because it's underfitting. It's not even be able to fit the training data. And this is because there are some nonlinear patterns that we need to capture in order to perform regression for this data set. Now we're going to consider 3 different approaches to achieve this, to capture such nonlinear patterns. The first is going to be regression trees, the second one is tree ensembles, and the third one is neural networks. In regression trees, what we do is we build a binary tree where the leaves correspond to different subsets of the feature space. So here the feature space is 2-dimensional because we have 2 features that are the day of the year and the hour of the day. And at each of these leaves, there's going to be like a subset. We're going to partition the feature space into disjoint subsets. And each of these subsets is going to correspond to one of these leaves as color-coded now, as I'm color-coding now. Okay, so now what is going to be the temperature estimate in each of these subsets? It's going to be constant, and it's going to be given by the average of the training temperatures within that subset. This is what this looks like, because that's the optimal thing to do if you want a constant estimate within each subset with respect to the residual sum of squares, which is, by the way, the same metric that we're optimizing when we're doing linear regression using ordinary least squares. Okay, you can see here the different estimates for each of the subsets. Imagine now that we want to use the tree to estimate the temperature on August 19 at 3 a.m. That's day equals to 251 and h equals to 3. Then, because the day is greater than 65, we have to go that way in the tree. The day is smaller than 296, we go left. Then we go right because it's larger than 144. And finally, we go left because the hour is less than 8. And we get an estimate which is 19 degrees, which we can completely explain, right? The estimate is equal to 19 degrees because we're in that subset, because the day is between 144 and 296, and the hour is between 0 and 8. So there's an interpretable explanation of why the regression method is producing this estimate. You might be wondering, how do we build this tree? Well, we build this tree by adding these bifurcations. And by adding a bifurcation, I mean you have to choose a feature and choose a threshold for the feature, and we add them one by one to minimize the residual sum of squares, which again is exactly the same metric that we are minimizing when we do ordinary least squares. But now, of course, the estimator has a very different structure because of the design of the regression model, which in this case depends on a binary tree. In the case of ordinary least squares, it's just linear coefficients that multiply each of the features. If you look at the training and test error, we see that the training error becomes very small as we increase the number of leaves in the tree, as we add more and more of these bifurcations, but the test error starts to increase. So we're starting to overfit. And this is a common phenomenon with trees, which are great models because they're interpretable and they're very simple, but they tend to underfit when they don't have a lot of leaves, and they tend to overfit when they have a lot of leaves. In order to address this, it turns out that you can combine multiple simple trees to obtain very good estimators that are often state-of-the-art when you have problems with like tens or hundreds of features. There are 3 main strategies to achieve this: bagging, where you average trees that are trained on resampled data sets, resampled versions of the training data set obtained via bootstrapping. Random forest, where you do exactly the same thing, but you modify how you build the tree so that when you add bifurcations, you only consider a random subset of features in order to get more diversity in your trees that you're averaging. And finally, boosting, which combines complementary trees that fit residuals of previous trees. I will explain in a moment how that works. Okay, let's start with bagging. In bagging, basically, we sample. So here we have 8,700 temperatures from 2015. What we would do to obtain a bagging estimator is we would sample 8,700 temperatures uniformly at random from this data. This would give us a new bootstrap data set, and then we would fit a tree to that bootstrap data set. Then we would repeat, we would get another bootstrap data set with 8,700 other temperatures resampled from the training set, and we would build another tree, and then another tree, and then we have a bunch of those trees, we just average them, and that's our bagging estimator. This is what the trees look like. The models look like, the individual trees and the estimator. These are their training and test errors. We observe that when we average, what happens is that the training error of the bagging estimator is better than the training error of the individual trees, and its test error is also better than most of the individual trees. So we have improved both the training and test error by aggregating these trees trained on the different bootstrap datasets. We have improved the error, but now we have a model that is much more difficult to interpret because now it's an average of 32 different trees, so it's much more difficult to explain why a certain estimate is produced. This is a common problem in sophisticated machine learning models that are able to capture nonlinear structure very well, and it's not restricted to bagging. This also happens from random forest, for boosting, and for neural networks. Oh, I should have, I gave it away before showing you. It's no longer interpretable. So a problem that bagging has is that because we are resampling from the same training data set, the resampled data sets tend to be similar, and hence the individual trees tend to be similar, which is sometimes not great because we're kind of averaging them to get basically there's not enough diversity when we average them to build the regression estimator. In order to address this, what we can do is when we're building the tree and adding bifurcations, we can consider just a subset of the features, a random subset of the features, to force the trees to be different from each other. This is what we did in this case for the same bootstrap data sets. And as you can see, I think it's the first tree is very similar to a third tree for bagging. That's no longer the case when we apply random forest. Okay. This randomization, when you add all the trees that are all the randomized trees that are fit to the different bootstrap data sets, that ensemble of trees is called a random forest, which is a beautiful name. And here it is. For our data set, when we do this, because of the randomization, the error of the fit to the data of the individual trees becomes worse because we're forcing them to use subset of random features, but overall the average becomes better because we're averaging more diverse trees, and this also improves the test error. Finally, boosting is a very different strategy from bagging and random forest. In bagging and random forest, we combine trees that are trained independently on these bootstrap data sets. In boosting, you try to build a complementary tree instead. The way you do this is by considering the residual of the previous combination of trees. We will see in a moment what I mean by that. But you scale down the individual contributions to avoid overfitting. This is very important because otherwise this boosting strategy can overfit very easily. It's better to just take a look at an example. Here is our training data set. We begin by fitting a tree to the data set. We're concerned that the tree might fit too much stuff from the data set, so we scale it down so that it cannot overfit as much. And then we compare it to the data set and produce a residue. The residue is still quite similar to the training data precisely because we have weighted down the tree to prevent fitting too much structure. Now we take this residue and we fit another tree to that residual. This is the tree. We scale down the tree, combine it with the previous scale down tree, that is our boosting model with 2 trees, and then we compare it to the original data. And little by little, this boosting model that is obtained by combining these scaled down trees that are trained on the residuals, little by little, it's going to capture more and more structure from the data, but in a pretty smooth way because of this scaling down operation. Otherwise, it would aggressively overfit the training data, and we end up with our boosting model. When we look at its performance for our specific data set with respect to the 2 other approaches, it's actually much better. So this is the training error of the boosting method. So it's able to fit the training data better than the random forest model, which is here. And it also has a much better test error. This is the test error of the boosting method, and this is the test error of random forest. If you don't use this trick of downscaling or scaling down the trees so that they don't overfit, boosting will actually overfit very aggressively. Maybe I'll use another color. So this is what happens, this naive boosting where you're not scaling down each component of the boosting model, and it actually really overfits the test data because you're overfitting the training data basically from the beginning. So this scaling down of the individual trees is actually very important in boosting. And now we have reached our final model of this whole video, which is neural networks. Neural networks are nonlinear functions that are implemented by interleaving linear, or rather affine transformations, because we're going to have additive constants, and nonlinearities. Let me show you an example that we're going to apply to our temperature estimation problem, where we had 2 features. The 2 features are combined linearly, or rather affinely, because there's going to be additive constants, to produce some hidden variables. This is the first layer of the neural network. Then those hidden variables are fed through a nonlinearity. A popular nonlinearity that I'm using here is the rectifying nonlinearity that only lets the hidden variables through if they are greater than 0. And then those are combined again linearly with an additive constant to produce the final estimate. All of this is a layer of the neural network. You can actually have several layers, but I didn't have space here to show you. Now, the parameters of the neural network are the linear coefficients and the additive constants in each layer. Those are estimated by minimizing the residual sum of squares, which is exactly the same cost function that we use in regression trees and in ordinary least squares. So it's funny how we use the same cost function, but we obtain very different models because of how we're actually building the regression model. And we minimize it on the training data, typically by separating the training data into batches and performing gradient descent with respect to the coefficients on each batch. This is called stochastic gradient descent because it's a stochastic approximation of the residual sum of squares over the whole data set. And this is done because usually the data sets are very large, and it would be too computationally expensive to do this on the whole training data. For our very simple model that just has one hidden layer, the training and the test error are actually the same roughly as the epochs proceed. An epoch is basically when we go over the whole training set and we update the coefficients with respect to the whole training set. These are the linear coefficients and additive constants that are learned in this way for our example. And we actually see that this very, very simple model learns that with respect to the day of the year, the temperatures first increase and then decrease. The training error is much, much better than the training error of the linear model, and it's on par with, it's better than the regression trees, on par with the ensembles, the tree ensembles. But how can we improve the model? Well, this is in the deep learning paradigm. What we do is we increase the size of the network, we make it larger and deeper, and ideally we'll train it on a larger data set. In this case, we don't have a larger data set, but we're going to see that this strategy can actually be beneficial even for smaller data sets. So we're going to use a 4-layer network with 100 hidden variables. in the intermediate layers, so that the number of parameters that we have to learn from the data is actually equal to 20,600, which in traditional statistics would sound completely crazy because we only have 8,700 data points. So, but what about overfitting? Well, if we look at how the training and test error of the neural network proceed, indeed we do observe overfitting if we wait for too many epochs, but here we actually see a pretty good test error. There's definitely some amount of overfitting, but the test error seems to be very good. And that's a common phenomenon in deep learning where you over-parameterize massively, and then you monitor the held out error, and you realize that this over-parameterization sometimes allows you to learn complex nonlinear functions that do generalize well to the test data, but you have to prevent overfitting by stopping training sufficiently early. If we don't do that by epoch 5000, we overfit quite a lot, although the test error, realize, is not so bad. It's still the same as in the simple model, but we are clearly overfitting. If we stop before, we get a better test error because we're reducing overfitting with this early stopping strategy. And this is the estimate that we obtain, which learns about certain patterns, like, for example, the temperature going up and down with respect to the day, and in this direction, with respect to the year, and in this direction with respect to the day. There is probably some amount of overfitting, but again, the test error is better. Is much better than with the smaller model. So hopefully this illustrates the potential of neural networks that are often able to learn complex nonlinear patterns in a very effective way, but also the dangers of overfitting the training data. So we have explained very different strategies to perform regression. We began with linear models, which included ordinary least squares, rich regression where you avoid overfitting by adding an L2 norm penalty, and the lasso where you obtain sparse coefficient estimates by incorporating an L1 norm penalty. And then we talked about nonlinear models, and the three strategies that we discussed were regression trees, tree ensembles, which included bagging, random forests, and boosting, and finally neural networks and deep learning. And that's all I got. Thank you very much.